Okay, so today we will finish with the last lecture in which we will discuss the general model for algal growth. We will finish the discussion concerning the general model for algal growth, and we will discuss further a little bit the concept of nutrient limitation, or in general the concept of growth limitation. As you may remember, we have said that unlimited growth is a biological nonsense. So if you want to describe in a meaningful way the growth of a population in ecology, you shall always include the fact that growth is limited by the availability of resources for growth. Yesterday, we have seen that the very general model describing algal growth is the one presented here. So we write that the variation in time of the concentration of algae that may be milligram of algae per liter or milligram of chlorophyll A or some other proxy indicator of the quantity of algae is equal to a series of parameters of some models, a positive contributor one that is referred to the growth rate, mu, and negatives or limiting effects due, for example, describing respiration, exudation, non-predatory mortality, and settling, that are processes that take away algae from the algal pool, from the population. These parameters are multiplied by A, that is the concentration of algae. So this makes, at least for the moment, this is a first order linear differential equation. Linear unless the concentration of algae appears somewhere else into these submodels or parameters. Minus the effect due to the upper trophic level that we may call grazing. And grazing is a measure of how much of the algal material is taken away from the system by upper trophic levels that are feeding on this population. So mu is the growth rate, or R is the respiration rate, S is the exudation rate, and non-predatory mortality, S sedimentation, and Z the grazing. We have already anticipated that, as it is customary for all these parameters or submodels, we may write, for example, let us explicitate the growth rate. We may write that the growth rate mu is equal to a maximum growth rate at the reference temperature, and very soon we will see what we mean by reference temperature, multiplied by a series of what we call limiting function, FT, FRL, MCESy, silicates, and so on. These are all functions, these F's are all functions in the codomain 0, 1, meaning that if a function is 1, then you have no limitation. You have a maximum growth rate. If the function is 0, then you have total limitation. This is a first way of combining several limiting effects. Here we are combining the limitation effect due to temperature, but through a function of T, the limiting effect due to light through a function FL, and the limiting effects or limitation effect due to the presence of nutrient F and P, C, and silicates. So these are functions. This function may be a function of the concentration of nitrogen, phosphorus, carbon, or silicates, or some other elements that are fundamental for the synthesis of bioorganic molecules. Let's first of all give a look to the temperature dependence. So how we include into our model the fact that temperature may change dramatically the dynamic of the system. Okay. In order to include the effect of temperature on growth, we have three different approaches. The first one is the linear approach in which we build our function. Please note again our limiting function ft. Please note that this is a value that is smaller than 1 and larger than 0. Of course, t min minus t min is larger than 0 because t min is the minimum temperature at which the algae can grow. Tref is the reference temperature at which the algae grows at its at its maximum, so its growth rate is the highest. The other model we may employ is an exponential model in which we make a dependence, a Arrhenius-like dependence on the f function t on the difference between the reference temperature and the actual temperature, or we may employ an optimum formulation. In this case, limiting function f t is made as a function is made dependent of the exponential of these quantities. This is the difference between the actual temperature and the optimal temperature for growth, and Tx represents the minimum or maximum temperature allowed for growth, and then you have Tx minus the optimum as a normalizing factor for the optimum formulation of growth. If we plot these models for nutrient limitation, for temperature limitation to growth, then we have these three curves. The linear one, dashed lines, the linear links the temperature with the maximum growth rate in a linear way. Then we have an exponential formulation, and then we have an optimum-like simulation. So we have a maximum that is comprised into an interval. Please note that in the mean or in the central interval of temperature ranges, let's say between 20 and 25 degrees, so this area, the three models are coinciding, so are coincident. So the three models are equals around the range of the optimal temperature, and then you will have differentiations on the limiting effect in outside this center range of optimum temperature. These three different models are employed depending on the composition of the algal pool. In general, we may say that if the algal pool is composed by only one algal type, we shall employ the optimal formulations, because the optimal formulations is based on the assumption that there is an optimum range of temperature in which you have the plant, the algae that is growing. In our cases, and in particular, if we are in a condition in which our algal pool is composed by several different types of algae, so with different effects on the algal growth linked to temperature changes, then it might be the case that you need to employ or a linear or an exponential curve, depending on the fact that there is or there isn't a predominant algal species in the algal pool. So if there is a predominant algal species, or you will then employ an optimum temperature model. If you do not have a predominant algal species, then you shall go back to the other two models, linear or exponential. This has to do with temperature. Now, let's give a look how do we introduce light dependence on the growth rate of algae. Again, please note that here we are dealing with a sum model. Growth rate mu is equal to a maximum rate at the reference temperature T multiplied by our limiting function. Here we have a limiting function for temperature that may be, as we have seen, exponential, linear, or optimum. And we have a limiting function for the presence of light, and we have a limiting function for the presence or absence of nutrient. Typically, the light dependence may be described by two submodels. The first one is the classical Michaelis-Menten equation. It is a saturation-like behavior in which the function for algal growth limitation due to presence of light is dependent on a parameter KL, that is the so-called semi-saturation constant. This means that when the intensity of light is equal to KL, you will have that the function will, the limiting function will have a value of 1/2 or 0.5. So you will have that when the intensity of light is equal to KL, the algae are growing at half the maximum possible speed of growth. We have another formulation that is a little bit more sophisticated, that is the optimum or still formulation. We are still talking about light limitation, so we are describing the function FL. In this case, in the case of the optimum or still formulation, we may say that the limiting function Fe, that is a function of intensity of radiation arriving onto my ecosystem, is equal to the ratio between the actual radiation and the optimal intensity radiation multiplied by an exponential factor. Again, that is function of this same ratio in actual intensity of radiation normalized by the optimal value of intensity. Now a question arises, of course, how do we estimate the optimum values of intensity, the optimum radiation for light growth? And this optimum, of course, is a function of time due to the fact that, as you know, the quantity of solar light that arrives to your ecosystem is depending on time. We have seen several methods, several models for describing this. We have seen an astronomical models that describe this in terms of the latitude, so position on the Earth, and in terms of the solar declination, so moment of the year. But we have also seen a more detailed model, that is a sinusoidal model, that may be employed for smaller time scales. In particular, from experimental observation, we may plot growth rates as function of light intensity, and we may identify two main behaviors, main different behaviors. The first one is the saturation-like behavior. So this is the Michaelis-Menten model, in which we employ a saturation conditions, which means that as the light intensity grows, you will have an increase in growth rate of the saturation level. And the second behavior is that of optimum behavior. In this case, you shall use the still formulation. In this case, you may say that after the maximum growth rate is reached while light intensity is increasing, there is a kind of photoinhibition effect due to the fact that, as we have seen, in some cases, even too much light may be detrimental for growth rate. So there are some algae that grow well at a certain light intensity, and when the light intensity increases, they start to slowing down their growth. So there is a kind of photoinhibition effect. Okay, so for the calculation of limiting function FL, so the effect of light on limiting the growth rate, you shall integrate the previous ones, so these models. Please remember that light intensity E depends on the day of the year, on the latitude, and also on the depth at which you are describing your model, at which you are describing your system. And by now, you know that in this case, the depth shall be taken into account by Lambert-Beer light Lambert-Beer light absorption phenomenon or light extinction phenomenon. For the calculation of the FL, you shall remember that you have to integrate the previous models over the depth and the photo period. So over the depth and over the time in which the portion of the daytime in which you have light. In the case of these integrals, for the saturation curve, you obtain for the limiting effect of light with two models. The saturation model is the first one, in which there is a function depending on the photoperiod, Fp, and a dependence of the depth at which the process is being observed, and a parameter gamma that depends on the fact that you have light attenuation or light absorption due to the Lambert-Beer model descriptions. Okay, so these are the general model you shall employ for light limitation. Now let's give a look to the other fundamental concept, that is that of nutrient limitation. What does nutrient limitation mean? Of course, as we have said, growth is possible as far as there are the availability of resources that are necessary for growth. So besides the optimality condition linked to temperature and the presence of the basic resource in terms of energy that has to do with the light, with solar radiation, you shall also take into consideration the fact that the availability of nutrients, like for example phosphorus, nitrogen, silicates, iron, and other elements, may be also relevant, may be also significant in order to influence the growth rate of the algal population. For phytoplankton, mostly we have carbon, hydrogen, oxygen, nitrogen, phosphorus, silicates, and sulfur as limiting elements. Of course, carbon, hydrogen, and oxygen are seldom limiting, because you may know that, for example, hydrogen is the most diffused element in our universe, so you will never find condition in which there is no hydrogen available. The same is for carbon, especially in the biosphere. You will find carbon everywhere. In the atmosphere, trivially, you will find carbon, for example, in carbon dioxide, while the situation for the nutrient, in particular nitrogen and phosphorus, is a little bit more complicated and more sophisticated, more delicate in order to evaluate the effects. In general, we start by observing that organic matter has always kind of a fixed stoichiometry. Do you remember when we introduced the model, the metabolic flow model? One of the basic assumptions was we are what we eat, meaning that the composition of the biomass produced by a living organism is in general very similar to the composition in stoichiometric terms of the food or the resources on which the organism feeds on. In general, the fixed stoichiometry for organic matter tells us that to 1 atom of phosphorus, you shall find 16 atoms of nitrogen, then 106 atoms of carbon, 110 atoms of oxygen, and 263 atoms of hydrogen. So this is a way of formalizing in chemical terms, based on the stoichiometric description, the fact that all biological matter has the same composition. So then we are left with the problem of combining different nutrient limitation effect, or more in general, different growth limitation effect. By employing the fixed stoichiometry model, we may say that the limiting function for nutrient availability is the classical Michaelis-Menten function that we have studied in enzymatic processes, because we have said that there is a striking analogy between enzyme, chemical kinetic of enzymes, and the chemical kinetic of bacteria. In this case, bacteria plays not only the role of a product, but also the role of enzyme, the enzymatic process. So in this case, we shall employ the Michaelis-Menten function for the particular nutrient. But what if we realize that there are more than one limiting nutrient for my algal pool? In general, the first thing we do, we multiply the limiting function as we have done here. Here we are simply multiplying different limiting functions. This is an effect that tries to describe the synergetic effect of multiple limiting processes. So we may multiply the different limiting function, or more often you may find a so-called Liebig's law of minimum, in which you assume that the important limiting function for the process that you are studying is that of the minimum value of the pool of the limiting function. So this is as to say that who is limiting the growth is a nutrient that is present in less quantities. Please note that concerning the particular element, nitrogen and phosphorus, our knowledge on the dynamic growth of algae in water ecosystem tells us that in case of fresh water ecosystem, so surface water bodies, typically the limiting nutrient is phosphorus. Typically the limiting nutrient is in a freshwater ecosystem is phosphorus, while if we look at saltwater ecosystem, the limiting nutrient is typically nitrogen. Why this? Because saltwater ecosystems are ecosystems in which the benthos, or the sediment part of the ecosystem, play a very important role. The sediment has a memory, keeps memory of a past story of a system, and in particular keeps memory in terms of nutrient concentrations. And while nutrients like nitrogen or nitrogen forms are mainly dissolved in the water column, on the contrary, phosphates or phosphorus quotas of a nutrient typically go with the solid transport. So what happens is that in a water ecosystem, in which you have a water column that may be influenced by phosphorus loads, when suspended solids settle onto the benthos or into the sediment, then a certain quantity of phosphorus will be stored into the sediment. And in this case, there are, by resuspension process, that are the inverse process compared to par rapport to settling. So resuspension, by resuspension, you may have transfers of phosphorus from the sediment onto the water column. While, for example, in the case of freshwater ecosystem, phosphorus may become limiting because phosphorus generally is brought into the system. And when I talk about freshwater ecosystem, I'm thinking essentially lakes. And in the case of lakes, phosphorus is brought into the lake through the solid transport, and maybe only in the case of surface water ecosystem limiting, may have a limiting effect due to the fact that, for example, the solid transport does not contribute in a large enough way to the nutrient balances. we will be more precise when we will introduce the rate-field ratio concept. Other way of combining nutrient limitation, besides that of multiplying the different limiting functions, so the synergetic approach, are those of finding the minimum, so the Liebig's law, or we may, in some cases, compute the harmonic mean, and also in some cases compute the arithmetic mean of a limiting function. Or this way of evaluating the total effect of multiple limiting factors are, in one case, we are overestimating the limiting function that have displayed the minimum value. What is the effect of course, let us focus on the Michaelis momentum limiting model. We may write that the limiting function of the concentration of nutrient as this saturation effect, meaning that while nutrients tends to grow, limit for n that tends to the infinity of this function, you obtain exactly 1. So the limit value for infinite nutrient growth for the limiting function is 1, but we have then another important parameter, that is the semi-saturation constant. What does the semi-saturation constant represent? Semi-saturation constant represents the concentration of nutrient at which you have that the growth rate is exactly the half of the maximum growth rate. So given that this function are in the column in 0, 1, you will have that you by simply substituting Kn into n in this equation, you obtain that f Kn is equal to 0.5 or 1/2. Okay, so this is the way you read the Michaelis-Menten function. Okay, here by implying these descriptions, we are again, as it is customary when we are in the conceptualization phase of a model, we are trying to simplify to get more simple. This is why we try to hinder of the complexity of such articulate process into the fact that we try to include only models with a limited number of parameters. In the case of Michaelis-Menten function, the parameters are the saturation, semi-saturation constant, and the maximum growth rate. We may be a little bit more detailed and or more specific, and this is not a matter of let's see, it is not a matter of wanting, willing to be necessarily complex, but it is a matter of willing to describe some observation, and I will soon give you an example. We may subdivide the growth dynamic process into 2 phases, so a 2-step process. The first phase, it is the uptake process that is influenced by external concentration, external to the cells, and internal to the cell concentration of nutrients. So the first part, the uptake part, depends on how much nutrients there are available in the, for example, in the water column, and how much nutrient do you have to the internal part of a cell. And we may describe, say, we may include a second process that after uptake describe essentially the growth process, but depends only on internal quota. So growth depends only on endogenous parameters to the phytoplankton cells, so how much internal quota of nutrients in the cytoplasm is available for biological processes to take place, while the uptake process, as you can imagine, depends on the difference in concentration between the surrounding environment and the internal part of the cell. And during the uptake process, we describe the fact that due to the fact that there are differences in concentration in the cytoplasm, so in the internal part of the cell, and between concentration in the internal part of the cell and into the water column, we may compute a different limiting function. In this case, this limiting function is made dependent on two concentrations, Q, that is the internal concentration, and C, that is the concentration, external concentration into the water column. So the uptake part of a process may be described by limiting the process by this kind of equation. Again, this is a Michaelis-Menten-like approach concerning external concentration, while it is a slightly different limiting approach concerning internal concentration. In particular, internal concentration, we employ two characteristic concentration, that is the maximum possible concentration of a nutrient into a cell, that is, of course, a characteristic of a particular cell, and also the minimum concentration possible into a cell, again, a characteristic of a cell. For the growth rate, instead, limiting effects on the growth rate, on the growth part of the second step of the process, you may include, describe it again by, for example, a Michaelis-Menten approach in which you, instead of using concentration, internal concentration Q, you simply use the difference between the actual internal concentration and the minimum internal concentration, or you may have these other two formulations, and you may decide which to apply according to your observation and according to what you know about the physiological characteristics of the algal population you are studying. Okay, I was telling you that this is not how do you say, an aleatory effort, or because we are really found ourselves sometimes in phases of these kind of processes that need a two-step description, a two-step dynamics description. For example, look at this graph. These are experimental data. We have a continuous line describing concentration of chlorophyll A, so how many or how much algae are present, or other lines corresponding to these stars, in which we are describing the nitrogen assimilated, and other lines in which we are describing, for example, phosphorus concentration. So what you may observe by this kind of situation, here we are plotting assimilated nitrogen or phosphate or chlorophyll A. Chlorophyll A is the continuous line, while assimilated nitrogen and phosphates are the other two lines. What it happens that in the beginning of spring, we see that there is a significant algal bloom, what we may call the first bloom. And after we see this first algal bloom, we have a large population of algae that is continuing to consume nitrogen and or phosphorus, so that they continues growing up to a maximum point, and then the algae start dying because the nutrients are becoming scarcer and scarcer. This happens until we start being mid-summer, and in mid-summer something unexpected happens, but there is a second algal bloom. What does this mean? How is it possible? Look at nutrient concentration, they are continuously decreasing. How is it possible that in summer, in June, you have a second algal bloom? This is possible due to the fact that the assimilation process and so the uptake process and the growth process are separated even in real algae or in real bacteria, photosynthetic bacteria. What happens is in real living objects is that in condition of large quantity of nutrients, these bacteria do what they call luxury uptake. So they uptake a lot of more nutrients for what they need compared to what we need for growth. So they tend to store into the internal part of a system, internal part of a cell, significant quota of nutrients, so that when the algae stops absorbing nutrients from the surrounding environment, because nutrients are becoming progressively scarce, then they may start employing the luxury uptake quota, in which, so they, in this case, growth is sustained. We say that growth is sustained by internal quotas. And then we may say these figures comes from lake observation, but lately, you going toward winter, autumn, and then winter, we have that the quotes of nutrients increase, quotes of available nutrients increase due to cycling of nutrients into the system. So we have elements that die and give back nutrients, make nutrients available for the algae to absorb and continue growing. Okay, so this is the two-step process. Please note that this is a question as well. Can you please describe the two-step process for algal growth? Of course, we shall note that the possibility of growing this system, very simple system, and I'm thinking at bacteria, for example, blue-green algae that are performing photosynthesis, depends on the availability of the different types of nutrients. Let us focus again on nitrogen and phosphorus. Then the bioavailability of these nutrients depends on their forms. In particular, for nitrogen, we may say that the organic part is dissolved or particulate, while the inorganic part may be ammonia nitrate and nitrate. Concerning nitrogen, the most available forms of nitrogen are ammonia and nitrate. I recall you that ammonia is NH3, while nitrate is NO3. So ammonia is much smaller than nitrate in terms of molecular dimension. This means that ammonia will pass more easily through the cell membrane. This means that these elements, these photosynthesizer will first of all employ all the ammonia available, and then they will switch to nitrate when the ammonia pool starts to be depleted. Slight different consideration concerning phosphorus. In the case of phosphorus, again, the organic form are dissolved and particulate. The inorganic form are orthophosphate and polyphosphate. Again, for a question of molecular dimensions, the orthophosphate, it is the immediately readily bioavailable form of phosphorus. Polyphosphate are larger, so we need some more processing in order to be made available for metabolic process. for metabolic growth. Please note that lately it has become evident that there is another form of phosphorus that may be very relevant in terms of nutrient limitation, meaning that it might reduce the limiting effect of the absence of phosphorus, and this form is the colloidal form. It is colloidal. It is a form in between a dissolvent and particulate, and it is a form that, especially in a wastewater treatment system, you may become a key role, may play a key role in the limiting effect of nutrients. So sometimes you may need also to include into your limiting effect also the quota linked to colloidal phosphorus. A way of putting numbers into this consideration is that of converting the fixed stoichiometry models, so the one that tells us that we have in organic matter, we have 1 atom of phosphorus, 16 atoms of nitrogen, 100 atoms of carbon, and 110 atoms of oxygen, and more than 260 atoms of hydrogen, is that of computing the Redfield ratio. I think you have already heard about Redfield ratio. Redfield ratio is the ratio between total nitrogen concentration and total phosphorus concentration. You may calculate the Redfield ratio in moles or in weight. In the case of the weight calculation, you simply have that due to the fact that 1 atom of phosphorus, you have 16 atoms of nitrogen. Then in the case of moles, if you have 1 atom of phosphorus, 16 atoms of nitrogen, then the Redfield ratio expressed by moles ratio is 16 to 1. While if you employ the weight of the molecules, the ratio, Redfield ratio, it is 7 to 1. It is important to notice that the Redfield ratio gives you an immediate estimation of who is the limiting nutrient. In particular, if you have a Redfield ratio calculated in weight that is larger than 7, in this case, you may say that there is a lack of nitrogen into your system. So there is an abundance of nitrogen into your system and a lack of phosphorus into your system. In this case, in the case of the Redfield ratio is larger than 7, you may say that phosphorus is the limiting nutrient. This is the typical case in freshwater ecosystem. While on the contrary, if the Redfield ratio is smaller than 7 in weight, then in this case, it will be nitrogen, the limiting nutrient. And as I told you, this is the typical condition in saltwater ecosystem. Okay, we said that nitrogen is limiting in saltwater ecosystem because in saltwater ecosystem we have the sediment that is always providing phosphorus. So we have a sediment that in its solid part performs as a reservoir for phosphorus. You calculate the Redfield ratio often by using total nitrogen and total phosphorus. However, you should be aware of the fact that not all forms are equally bioavailable, as we have just said. So, depending on the condition of the system you are going to model, you may decide to employ other estimation of the quantity of nitrogen and phosphorus. You have also to take into account that you may be in condition in which you have a two-step dynamics process, in which you may have Lux reuptake, or you may be in condition in which even if the concentration in water is low, uptake could be balanced by other processes. Like example, as I told you, the flux from the sediments that may influence the red-fill ratio in terms of availability of nutrients. The limiting nutrients could be harder to reduce than others. For example, this is the case of phosphorus in lakes. Another way of measuring the effect of nutrient, of the limiting nutrient, is that of employing the Platt index. We have two forms of Platt index. An absolute form, here we are evaluating how much the growth rate parameter mu changes as a consequence of changes in the concentration of nutrients, nitrogen, over the concentration of nutrients in phosphorus. So here we are evaluating which of the two nutrients, nitrogen and phosphorus, are more affecting the growth rate parameter. Please remember that the growth rate parameter is given by a constant, typically mu max at the reference temperature, and this constant is multiplied by the synergic effect of different limiting functions. In this case, a limiting function for nitrogen, limiting function for phosphorus. And in the evaluation of the absolute Platt index, you shall employ the Michaelis-Menten formulation for the limiting effect on growth of the nutrients, nitrogen and phosphorus. The second form of the Platt index is the relative form, in which we do the same evaluation, but we normalize it by the total values of nitrogen and phosphorus. This is especially important when we have significantly different effects, limiting effects linked to the two nutrients. So in this case, it is better to employ a normalized or relative index to evaluate which is the limiting nutrients. We have anticipated that there are limitations or effects due also to other nutrients, in particular silicates or oligoelements like iron, or sometimes carbon, but this is rarely limiting. For example, again, these are these are data, figures that comes from experimental observation of a coastal area. In this case, here we compare the concentration of algae in the water body and the concentration of silicones. In this case, for example, we have a higher concentration of silicones, the blue line, that corresponds then to a bloom in algal growth. These are algae that depends on the presence of silicate. You may remember from the discussion we had yesterday that these algae are typically diatoms. So that when these algae starts to grow, they start consuming silicon, and then after the concentration of silicon drops, also the population of algae tends to drop as well. So this is a clear demonstration that we have nutrient limitation due to silicates, also due to silicates for algae. The silicon limitation has become an issue, especially in last part of the 20th century, let's say in the 50s, 60s, and 70s, starting from the 60s. For example, we have several data coming from very different ecosystems in the world, in which, for example, let's look at the first graph. In this case, we are plotting the silicon concentration, silicon over nitrogen concentration ratio. These are moles per moles. So this is a ratio, a dimension, quantity. In this case, you see that as the times increases, then you have a slightly decreasing effect of silicates to nitrogen ratio. What does this mean? This means that as time increases, silicon becomes scarcer and scarcer, so that this ratio tends to go down. So if you make a very trivial or gross description of this effect, see if I'm able to draw a line. Okay. In this case, you may say that we have a decreasing tendency of a ratio, silicon over nitrogen. This is what happens in the Irish Sea, that is a smaller part of the North Atlantic Ocean. What does this mean? This means that in the years, the effect of silicon limitation is becoming more and more relevant. This means that the population in the algal pool we are describing the Irish Sea is formed by a significant quota of diatoms of algae that need the presence of silicates in order to grow. We have other example of this silicon limitation, like for example, this is the Mississippi River. Again, we plot the silicon over nitrogen concentration, silicon over nitrogen concentration ratio, and we see that as time increases, we have again a decreasing tendency for the nitrogen, sorry, for the silicon to nitrogen concentration ratio, and the same in the Bay of Brest. So this forces you to ask yourself the question concerning what are the role of diatoms in this algal pool. So if you have this kind of data, then you shall realize that there is a significant role of diatoms into your algal pool that may affect the growth rate of primary producers. Okay. So up to now, we have seen the biological process of growth that we made, the model for describing the biological process of growth for algae, so phytoplankton. There is a question, possible question, primary production models, another possible question, growth, phytoplankton growth models. So these models you have to know because these are possible questions during the exam. Now let's give a look to how we treat the upper trophic levels. This means that now we want to describe the effect of the grazing process so the effect of taking away algae from your algae population pool due to the grazing effect of zooplankton, so of the higher trophic level. This is a copepods, an example of a very small zooplankton organisms. So this is not a bacteria, but these are a very, very animal, very, very. We are talking about microns or hundreds of microns, but anyway, very small animals. In this case, in order to include the effect of grazing, that is of course a limiting effect, so negative effect, we may model G by saying that G is equal to a grazing level depends from the reference temperature multiplied by an Arrhenius-like model describing the effect of different temperature onto the grazing process. And then, in this case, you may, for example, model more in detail, mortality, I recall you that in classical formulation, this is the non-predatory mortality. So we may write this with a NP, while the predatory mortality, that is again a negative effect, is included into raising factor. So in this case, you may write that the total mortality is equal to the non-predatory mortality plus a quota of mortality depending on the concentration of zooplankton corrected by an Arrhenius-like factor that corrects for the effect of temperature. We may immediately identify two very broad classes of zooplanktons or grazers. The first one is filter feeders. Filter feeders are grazers or animals that they stand still. So filter feeders are animals that they stand still with the mouth open wide or wide open mouth, and they wait for water to pass through their body, and they filter the water content in terms of algae present in the water. How do we model that? We model that by saying that the grazing effect is equal to the concentration of filter feeders, reference temperature, multiplied, for a function, a limiting function of the temperature, multiplied to a concentration of algae and the concentration of the filter feeders. So in this case, the quantity of algae taken away by the filter feeders is proportional by the quantity of filter feeders or zooplankton present and proportional to the concentration of the algae in the flowing water. This is the case for filter feeders. While for grazers, we have a slightly different formulation. In this case, the growth rate is equal to a concentration of grazers at the reference temperature multiplied by a limiting function for grazer limiting temperature, temperature limiting function for grazer, Ft multiplied only by the concentration of zooplankton or grazers. If you have several grazers that are feeding on the same algal pool, then you may explicitate this effect by employing different values of a grazing process, and you may summarize the effects onto a single value. Now, in particular, in the case of the zooplankton growth, given this definition, we may write that the concentration of zooplankton varies in time as an effect of the growth rate, again, this is the growth rate of zooplankton, respiration rate of zooplankton, exudation, non-predatory mortality of zooplankton multiplied by the concentration of zooplankton itself. So again, this is first order linear differential equation, minus a factor G, capital G, that describes predation mortality by the upper trophic level that are feeding on this zooplankton. Typically, there are fishes that are eating these small crabs or these small crustaceans, and you will include the effect of these fishes into the capital G factor. Okay, please note that in this case, we do not include a settling process because settling is less relevant because we are dealing with animals and not algae, not plants. And animals have the very nuisance property of doing what they want to do. So they possess free will. So they may be able to swim and to pass from the bottom part onto the surface part of the system. so that the settling effect becomes, in this case, neglectable, because these are animals that are capable to move themselves toward those parts of the systems in which they find most nutrient availability. Okay, we conclude our lecture by giving a very quick overview on the phosphorus cycle, that is the second very important biogeochemical cycle we shall look at. Again, phosphorus is a key element for life. It's one of the five most important elements found in living organisms. For example, 60% of bones are found in the form of calcium phosphate, but also is found in soft tissues. In particular, for energetic metabolism, you may recall that we have introduced the two molecules, adenine diphosphate and adenine triphosphate, that are phosphorus-based molecules that transport energy and make available the energy obtained by consumption to all the organisms present in the body, or to all the cells present in the body. Phosphorus is, of course, found in DNA and RNA. Phosphorus is present, for example, in the membranes, and by now you should know how important are membranes. For example, membranes, I recall you, are phospholipid structures that separate the internal environment of the cell from the external unstable environment of the surrounding conditions. Then phosphorus is very relevant, especially when there are humans involved in the story, because as you may imagine, phosphorus appears as an important element in agricultural activity, in which you may apply fertilizers, but also in industrial processes, for example, in detergents, medicines, and so on. You may have significant quantity of phosphorus. You may recall that in the 50s of the 20th century, sorry, in the 80s of the 20th century, 1985, we have a first phosphorus ban from the European Community. So we have a directive in which industries are requested or are induced to produce less phosphorus, because it has been recognized that phosphorus may be an important pollutant. Like, for example, we may see some figures, again coming from experimental observation of water ecosystem. We have an indication of decreasing phosphorus loads and aquatic ecosystem productivity. For example, let us forget this topmost graphics. Instead, let us give a look at the bottom part of the graphic. Here we are describing the effect of phosphorus, blue line. Sorry, of the phosphorus, that is the red line, onto the sardine. So, this is the sorry, I silenciate. Okay, this is these are figures. I'm looking at these bottom graphs. These are figures coming from the Northern Adriatic Sea, that is a portion of the sea that is the eastmost part of the Mediterranean, that is surrounding Italy. So we have, you may recall from the Monelli's lecture, modeling nutrient emission into river system. You may recall that in this part of the Mediterranean Sea, so the Adriatic Sea, we have a very important discharge coming from land, that is the discharge due to the Po River, 1,500 cubic meters per second in average. And these discharges bring down a lot of nutrients, in particular nitrogen and phosphorus, while you have on the with the blue line here, you have the concentration of sardines. Sardines is a small fish that is the basis of a trophic chain for salt water river ecosystems like is the Adriatic Sea. So by looking at these graphs, in particular by looking at the graph concerning orthophosphate PO4 concentration in tons in the years, so we see that around the 1986, when the first pre-ban directive from the European Community was issued, we have a dramatic decrease of the concentration or the quantity of phosphorus discharging into the Adriatic Sea. As a consequence, it is not very evident here because we have a small, an important lack of data concerning fishing of sardines. It is an indicator of the primary production because sardines directly feed on phytoplankton. And so we have a dramatic effect in the phosphorus load in the 80s, and then a stabilizing effect of the phosphorus concentration load in the subsequent years. In terms of fishing effort, we have quite of a stable effect after the 86. Of course, we have holes in this data series for two reasons. The first reason, around 89 and 92, you may know or you may not know, but in Europe we had a dramatic war in what is called the ex-Yugoslavian republics. So we had a dramatic war in the eastmost part of the continent around the Adriatic Sea. This has the consequence that during the war period, so between 89 and 92, we had a significant stop in the fishing activities, so that we have a real data lack in terms of sardine catches in the Adriatic Sea. We had also the same effect here in the 70s. I'm sure you do not remember. I instead remember because in the 70s I was a kid, and I remember we had a dramatic economical crisis in which we have a so-called gasoline crisis, in which we had to stop several industrial activities, for example, also fisheries. So this is just to say that anthropic activities in terms of fisheries stop, or industrial processes stops, or in terms of wars that makes fishing activity stop again, or in terms of policy that reduces the quantity of phosphate discharged by the land to the water system and to the water bodies, you have important effects also on several ecosystem conditions, like, for example, fish stocks of the first consumers, of the first trophic consumers of primary producers or of a primary production. Okay, now let's conclude this lecture by giving a very quick look at the phosphorus cycle. The phosphorus cycle, as we already said, is a slow sedimentary cycle. We do not have a gas phases like is in the case of nitrogen, in which we have a large reservoir that is the atmosphere. Instead, in the case of phosphorus cycle, that is a sedimentary cycle, where reservoir is found essentially, as I was telling you, in marine sediments. This is why phosphorus is seldom limiting in saltwater ecosystem, because in marine sediments are the storage or the sink for the phosphorus cycle. In this case, for example, you may have input, for example, linked to mining activities or anthropic activity, or you may have input due to weatherings of rocks or due to sedimentary deposits. So this is again settling. Of course, this cycle, as well as the phosphorus cycle, as well as the marine sediment processes, all require very long time intervals to happen, up to millions of years. We are talking, especially if we look at the effect of marine. What it happens is that the phosphorus cycle may be separated into two parts. A first part that is moving from the storages in rock and sedimentary deposits by weathering, or by erosions, or by resuspension, and a part that is linked to the biological activities of uptake that moves phosphorus from the sedimentary deposit into the biosphere. Of course, there is the main downward process that moves phosphorus from the rocks and sedimentary deposit through the phosphorus cycles into the biosphere, into marine sediments that are essentially produced by biological waste projects. Okay. Concerning phosphorus storages, we may say that only 1% is in the earth crust, and this is mainly in the form of calcium compost, calcium molecules, biomolecules, 95% of this 0.1%. So the fundamental part of these molecules containing phosphorus are phosphates. So in magmatic and metamorphic rock sedimentary deposits, marine phosphate beds may contain up to 80% of the potential phosphorus. This comes, for example, from, as I was telling you, wastes from the biospheres like guano from birds. That is the most ancient fertilizer source. Phosphorus in the environment is dramatic. So the dynamic of phosphorus in the environment is dramatically controlled by pH. In particular, inorganic phosphorus, but nearly always in the form of phosphates or orthophosphates ions, is of the phosphate forms. The orthophosphate ions is the most available, as we have said, most available form. pH play an important role by moving the reduced forms that are the most common reduced forms in the environment, but are H3PO4, H2PO4, HPO4 2 minus, or simply phosphate PO4 3 minus. For these elements, the percent of phosphates depends on the equilibrium between the phosphate and the reduced form depends on two optimal values of pH. In particular, the equilibrium is pushed toward the H2PO4 forms when you have a pH in the environment in the range between 4 and 5, let's say, or the equilibrium will be pushed toward HPO4 2 minus if you have pHs in the range 9 to 11. On the contrary, this optimal condition may change if abiotic conditions change in terms of pH or alkalinity. Okay. If you have any doubts, we can discuss a little bit more about how you read this plot. Typically, organic phosphorus is hydrolyzed into inorganic forms. Again, inorganic means phosphate. The dissolved quota, that is mainly polyphosphate with low molecular weights. The particular quota comes from essentially mainly polyphosphate with high molecular weight but are adsorbed to organic sediments or organic acids, esters. This is the particulate part, so this is the most significant part, the most significant processes that moves phosphorus, the solid transport. Then you have to take into consideration also the fact that colloidal forms that may be dispersed, phased with dimensions that are in the range 10 to minus 6 to 10 to minus 9 meters, so microns to angstroms, to 10th of angstroms, throughout a continuous phase is bioavailable, but typically this is secondarily bioavailable, meaning that living organisms or primary producers typically consume all the orthophosphate forms, and when the orthophosphates or the polyphosphate form are getting reduced, then they switch to the colloidal form. Absorbed phosphorus, it is accumulating in the lithosphere through suspended transport, through solid transport. The process is adsorption. It is a physically reversible process, but is not chemically reversible, or it is just partially irreversible, because you may recall that adsorption is the process of movement of dissolved substances from the water column into the solid parts of the suspended solid. And this process is only partly reversible, partially reversible. Phosphorus tends to form complexes with metal cations, and the substitution of water molecules or silicate ions in clays, for example, may enhance phosphorus immobilization, and this happens particularly at low pH values. Phosphorus has a strong tendency to adsorb, so lengthy transport through erosion, this is solid transport, and you do not have transport of the dissolved forms, for example, as is the case in leaching, and what is typical for the dissolved forms of nitrogen. Particulate phosphorus is not much bioavailable. So this means that phosphorus may be limiting despite its abundance. Sometimes it is more limiting than nitrogen, even if organisms need less phosphorus than nitrogen. The point is, this is what happens typically in freshwater ecosystem, is that even if there is some phosphorus, this quantity of phosphorus may be not enough for obtaining lead-free ratio equilibrium like for the production for the primary producers. Adsorbed phosphorus, the deposition released in water environments are governed by several factors that influence adsorption. You may recall granulometry. Adsorption increase with the fine fraction, so adsorption increase with the fine granulometry of sediments, because we have I recall you that adsorption is a surface process, so in more fine granulometry sediments, you will have more available surface. The organic substrates, but this is not a general rule. but we may say that organic substrates can absorb phosphates or block absorption sites on inorganic particles. All of these equilibrium conditions are driven by the redox potentials. So again, the redox potential or alkalinity or pH are all very relevant environmental conditions that may influence significantly the cycle of phosphorus. What are other factors influences absorption? Temperature. We have seen that temperature influences bacterial processes, which are those that have the ability of hydrolyzing organic phosphorus, of converting organic phosphorus into orthophosphate in organic forms that are available. For pH, there is no general rule. Okay, this is more in detail the phosphorus cycle. Here we are trying to put together all the things that we have said. For example, birds, fish, also dead fish or dead organisms produce phosphorus storages in rocks or in guanos or in bones. They're dead organisms. I recall you that organisms with scaffolds, skeletons, contain large quantity of phosphorus in the bones. When we have an equilibrium between erosion or weathering, that is a chemical, but maybe chemical, physical or biological processes, and causes a resuspension, that is a release of phosphorus from the sediment into the aquatic quota, into the water column. The reverse of this process is precipitation or absorption, so movement of dissolved quotas onto a suspended solid. When the exchange between the storages in the solid part, quota, rocks, guano, and bones is exchanged with the dissolved phosphate, which is inorganic through these two counteracting processes, precipitation, absorption, and or erosion, weathering, or resuspension. The quota in the dissolved part may be uptaken from primary producer and or may be converted from inorganic to organic part. Again, this goes to the marine sediment. While if you look at what happens to the dissolved quotas, these dissolved quotas goes into the food webs. Food webs means that there is a continuous exchange between plants, phosphorus in plants, that is transferred by algal growth, by grazing into animals, and then both plants and animals may release phosphorus to the bacterial pool in their waste bypass product of their metabolic processes, but may transport bacteria onto the marine sediments. Again, so the cycle may be closed this way. So, in surface water bodies, what are the sources of spillouts? Uncultivated soils, so this is surface runoff, precipitation, that means atmospheric deposition, or wastewater treatment plants. You may know that in standard condition, one adult produces 1.5 grams of phosphorus per day, or in condition in which there is no control on the phosphates in detergents, we may have also an important contribution due to detergents. But we have also industrial discharges or livestock activities like manure producers and so on. Then there are some diffuse sources. Typically, the agricultural fields in which you spread on manure are diffuse phosphorus sources. Internal loads transport from the sediments to the epilemium, This is very important in the case of lakes. You may remember one of the first models we have seen, it was a lake model in which we tried to describe a nutrification process whose currency of the model was phosphorus. So we may have diffusion of phosphorus into the water column that is controlled by pH condition or redox potential and so on. Turbulence that may cause direct transport or may recreate phosphorus gradients. Convections processes like bubbles, bioturbation. Bioturbation are living organisms that move sediments, low saturation capacity from the sediments, or, for example, very shallow water depths that make a strong linkage to, for example, the suspension model from the wind effects due to air masses flowing onto the surface of a water body to the sediment part of the water body or benthic part. This is resuspension that we have already introduced as a model, and that becomes particularly relevant, especially in shallow water bodies. It is finally also to take into account that the dynamic of biogeochemical cycles are very different from phosphorus to nitrogen. For the different nutrients are characterized, so the cycles of these elements for the different nutrients are characterized by different dynamics and time scale, and sometimes also for the red field ratio correction. For example, how far we are from the red field ratio. That is an ideal stoichiometric evaluation of the distribution of nutrients, but also on the timing of biogeochemical cycles. Typically, the timing of biogeochemical cycles for nitrogen is 40 days. This means that one atom of nitrogen typically employs 40 days to be returned to its source in the biogeochemical cycle of nitrogen, while phosphorus cycles much faster, meaning that the recycling times for phosphorus is in the range of 15 days. I would say in French, hebdomadaire cycle. Okay, I'm not going to discuss this model. This is a very trivial model. You can find it in the literature. This is the KC star model of nutrient abutment. This is applicable in wetland systems that are shallow water, freshwater system, or better shallow water system, for which you may employ these general models that describes the dynamics of several elements, and it is applicable by a plug flow first order assumption, and can be used for all pollutants like nitrogen, phosphorus, suspended solid bacteria, and so on. The parameters of this model are the wetland surface, the concentration in the inflow, the concentration in the outflow, the background forces concentration, the first order rate, constant cinetic. This is a calibration constant. It depends on temperature and, of course, the average flow through the system, but is measured by the discharge. The discharge through the water body, or the specific hydraulic load, but is the discharge divided by the surface of the water body. Okay, my friends, I think we can stop here now. It is 4 p.m., sorry. So we stop here and I wait for your questions, or I'm looking forward to meet you on Monday morning at 10 a.m. Yaoundé time to start a quick revision of all the concepts we are presenting during the class. I hope that it will be enough the morning of Monday. It might be possible we need also the afternoon of the Monday of Tuesday. Let's say the afternoon of Tuesday, just to close all the questions, because we will discuss the 60 golden questions. Please note that I made available these 60 questions onto the Moodle website of the class. So you can have an anticipation of these questions. And so you may prepare to demand me more deepening to the concept you find more difficult to explain. Or if you do not understand the questions, I'm expecting that on Monday, are you saying, hey, Prof, what do you want me to answer when you are asking such and such? Okay, in the meanwhile, I suggest Aisha, delegate, to start discussing possible dates for the exam. I will send the text of your exam to Mr. Kang by Monday morning. So on Monday morning, Mr. Kang should have at his hands the text of your exam. So he just needs to know which is the date you have decided for performing your examination. Okay, thank you very much for following my class. I now stay in the classroom for 5 minutes waiting for your question. And if you don't ask anything, I will close the class. And we will meet on Monday. If you have any urgent or any dramatic question or any information you shall or you'd like to communicate me, please do not hesitate to write me by email or to communicate with the delegates who has my WhatsApp contact and can contact me very quickly. Okay, thank you very much. I wait 5 minutes and then I close the class. No feedbacks from you, eh? It is a little bit sad for me. It is like speaking with a computer screen without anybody besides it. Do you think you will be able to study for this class? Do you think you will be able to pass the exam?
Yes, sir.
Mhm.
We'll study and ask our questions on Monday.
Okay. You're waiting for discussable questions on Monday, right?
Yes, sir.
Okay. Entonces,